Hello, my name is Stephen Pasteris, and this is my talk entitled Online Learning of Facility Locations, which is co-authored by Ting, Fabio Vitale, Shiqiang Wang, and Mark Herbster. First, we're going to give some intuition behind our problem and define the loss of a set of facilities. We have n sites, which are enumerated from 1 to n, and some user. For each site I, Ci is the cost to open a facility on that site, and Di is the cost of connecting the user to that site. So given we open facilities on a subset X of the sites, the sum of I and X of Ci is the cost of opening of facilities, and the minimizer across all I and X of Di is the cost of connecting the user to a facility. So the total loss is the sum of these two costs. We'll write this total loss as L of X, which has subscript opening cost vector C and connection cost vector D. Now we're going to define a facility location game, which is a game between learner and nature. Learning proceeds in trials T from 1 to T. On trial T, nature chooses an opening cost vector Ct and a connection cost vector dt. We note that capital C is an upper bound on the opening cost of any site on any trial, and capital D is an upper bound on the connection cost of any site on any trial. So nature chooses these vectors, and learner simultaneously chooses a set xt of sites. Learner then incurs loss of lxt with respect to the opening cost vector ct and the connection cost vector dt, which was given on the previous slide. The goal of learner is to minimize the cumulative loss over all trials. Note that choosing, in retrospect, the set x star that minimizes the total cumulative loss is the classic uncapacitated facility location problem, or FLP for short. So we're going to develop a randomized algorithm for learner, which has the following properties. The running time per trial is almost linear. It has an extra factor log n and an extra factor log t. And for any set x star of sites, the expected cumulative loss is given in the equation in red. So this bound is good, since the first term is a lower bound on the performance of efficient algorithms for the facility location problem, unless P is equal to NP. And the second term is close to, and often outperforms, the Hedge algorithm bound, which in this case is an exponential time algorithm. Let delta n be the n-dimensional simplex. We're going to reduce the facility location game to online convex optimization over the simplex, which is abbreviated to OCO. In this game, learning again proceeds in trials T from 1 to capital T. This time on trial T, nature chooses a convex function ht over the simplex, and learner simultaneously chooses a vector in the simplex. Learner then incurs loss of ht applied to pt. We'll play the online convex optimization via the classic exponential gradient method, abbreviated to EGM. This takes a parameter g, which is an upper bound on the magnitude of any component of the derivative of ht all over the simplex on any trial t. We're going to let the learning rate, eta, be defined by, as in the slide, which is a function of g, n, and t. Learner then chooses pt as given in the slide. The bound for the exponential gradient method is given in the equation in red for any p star in the simplex. So we're going to initially design an algorithm, FL bullet, which takes a parameter k and has loss bounded only with respect to fixed sets of sites which have cardinality k. So we're going to reduce this to online convex optimization, and for that we need a surrogate convex function f with respect to opening cost vector c and connection cost vector d. To do this, define upsilon as k times the ceiling of log t over 2. Then, given a vector d, a connection cost vector d, we define v1 to vn as an ordering of the sites such that the connection cost is monotonically decreasing over this ordering. Finally, given opening cost vector c and a connection cost vector d, we define fcd as given in the equation in red. Okay, so our surrogate convex function f has the following properties. Firstly, it's convex over the simplex. Secondly, the magnitude of any component of the gradient across the whole of the simplex is bounded above by c plus d times upsilon. Third, suppose we have some probability distribution p in the simplex, a probability distribution being equivalent to a vector in the simplex. So, letting x be a random set of upsilon sites drawn IID with replacement from p, we have that the expectation of Lx is upper bounded by f of p. Finally, the fourth property is that for any x star, set x star of sites with cardinality equal to k, we have that the minimizer across the simplex, the minimizer of p star in the simplex, of the sum of f with respect to ct and dt of p star is bounded above as in the equation in red. So the properties on the previous slide imply that we can reduce our problem to online convex optimization. So here g is equal to c plus d times upsilon. ht, which is the convex function selected by nature on trial t, is the function f with opening cost vector ct and connection cost vector dt. And xt is formed by sampling upsilon sites, IID, from a probability distribution pt, which was the output of the exponented gradient method. So the loss bound of the exponented gradient method implies that for all x star with cardinality equal to k, the expected cumulative loss is bounded as in the equation in red. We'll now design an algorithm FL circle, which has loss bounded only with respect to fixed sets of sites x star, but this time with x star with cardinality less than or equal to k instead of equal to k. We're going to do this via a reduction to FL bullet, and to do this with the same parameter k. To do this reduction, we add, on every trial, we add n dummy sites, each with 0 opening cost and a connection cost of c plus t, to form the input to FL bullet. We then take the output of FL bullet and form the output of FL circle by removing the dummy sites from the output of FL bullet. Of course, we can't output the empty set, so if this set is empty, then we instead output an arbitrary singleton set. So now we get the same loss bound as for FL bullet, except this time it holds for all x star with cardinality bounded above by k, instead of all x star with cardinality equal to k. Finally, we use a doubling trick to form our final algorithm. We're only going to give the gist of the doubling trick here. Consult the paper for the exact algorithm. But basically, we start by choosing a low value of k and then running FL circle with that parameter k until a certain cumulative expected loss is made. We then increase k, restart and run FL circle with the new increased k until a certain cumulative expected loss is made. We then increase k again and do the same thing. By continuing in this way, we get the bound which was given in the results slide. So to conclude, we considered an online learning version of the classic uncapacited facility location problem and developed an almost linear time online learning algorithm with performance guarantees. We would like to thank DIAS ITA for sponsoring this research. Thank you.